how close you can come, finding an actual CV. The other was a calculated CV. In our examples for the steam valve, the method here is the chart. And again, sizing the water valve, we can take a look at this and see that on the top we have the differential pressure. This is the pressure drop. In our example, using that same one, we wanted a pressure drop of 2. Now taking that and going down the 2 column, we go down until we hit our gallons per minute, or as close to it as we can get. In this case, 9.6 as close to the 10 gallons per minute as we can get. Moving then to the left, you'll see that the CV is written right there. In this example, it is 6.8. This method is very quick also, but not all the pressure drops that I need are shown. This chart is available in the green catalog. The next area to be covered is steam system sizing. As the same as in water system sizing, we have 3 methods. They are the formula method, the nomograph method, and the chart method. Each one of these will be covered in detail. Here's our first example, the formula method. In the example that we have here, we have 220 pounds per hour, and the system pressure is 10 psi. Let me explain the letters first. Q stands for the quantity of steam, in other words, in pounds per hour. In this example would be 220. The K stands for the amount of superheat. For most of our examples, we could ignore this. Down at the bottom, you can see 3 times the square root of, here's our pressure drop. And again, you'd have to go back to the pressure drop chart to determine what pressure drop you should have. Times P2. P2 is the pressure on the downside of the valve. As an example, if I have a valve here, and I have 10 psi in our example as you see, and my pressure drop is equal to 8, I have a 2 psi left over. That's P2. Now let's work this in an example. You have CV equal to 220 divided by 3 times the square root of, in our example we said 8 is our pressure drop, times our P2, and this again has to be in absolute. So you take the 2 psi plus atmospheric pressure of 14.7, and you have 16.7. Working this entire formula out, you will find out that the CV comes out to be 6.3. Here's the second method in finding the correct CV using steam. Here's a steam nomograph. Notice the columns that we have here. You have the pressure drop across the valve, the inlet pressure, the quantity of steam, and the CV. Here it's already drawn out for you. You can see the pressure drop we wanted was 8. The inlet steam was 10 psi coming in. Drawing a line between those, we have a new base point. From that point, you take that through your pounds per hour, or your quantity of steam, in this case 220, and you come to a value here of approximately about 6.5. So we have a CV of approximately 6.5. Here's the last method for finding the CV for a steam valve. Let's take a look at it. And that's the chart method. Notice at the top we have our inlet pressure. We are going to take the inlet pressure of 10. Now that column here is subdivided into 2 columns. Here it says 1 on one side of it and 8 on the other. The 1, or the one on the left, stands for 2 positioning. The one on the right stands for proportional control. In our example, we wanted proportional control for the steam valve. So we will go down the pressure drop of 8. going down this column until I hit my quantity of steam that I had. In our example, again, approximately 220. 215 is as close as I'm going to get. Taking this all the way to the left, the CV that I want is 6.2. Once you've determined a CV for either the steam or the water valve, you need to go to the valves to find out how close you can come, finding an actual CV. The other was a calculated CV. In our examples for the steam valve, we had a calculation of 6.3. It's very obvious then that you take the one closest to that. In that case, 6.2. So our calculated CV would be 6.3, but the actual CV would be 6.2 because that's what the valve has. In the water system, it's a little difficult because we had a CV of 7.0. Now that falls right between these two categories. Which one do you pick? That's a choice really up to you. If you choose the smaller one, you'll have much better control. But you run the risk of insufficient heating or cooling at design conditions. In other words, 10 days in January perhaps. If you choose the higher CV, you are oversizing a little bit. Therefore, you're not going to have as good as control. A rule of thumb, go to the closer. Let's go ahead and work out a CV problem. Using that problem that we showed for the pressure drop, let's go ahead and work out the CV for that same problem. Here we have the gallons per minute for a particular coil, in this case a cooling coil, and you can see that it's 291 gallons per minute. Pressure drop is 13 feet. But remember, we had calculated that out to really come out to be a pressure drop equal to 16.5 psi. Now putting that all together, we have 291, which is our gallons per minute. Divide that by the square root of 16.5. You'll come up then with a CV of 71.6. So CV in this example equals 71.6. I would then go to the catalog and find the CV that closely came to this calculated CV. Once a CV has been chosen, other considerations must be taken into account before you select a valve, and they're listed here. One is tight shutoff required? Does that valve need to shut off tightly against the flow? Next, will it match the fluid pressure and temperature limits? Some of the valves have a temperature limit of only 231. That needs to be checked out. Flow characteristic. Will the flow characteristics of an equal percentage valve or a modified V-port, will that be sufficient? Next, the body pattern. Does it need to be union end, globe screwed, or a flanged valve? Next, selection of the actuator. Will the actuator I pick fit on the valve that I'm choosing? Next, the close-off rating. The actuator that I do choose, will it close off against the flow of water in the system? The ambient temperature at the actuator. The actuator might have a limit, so you must be careful. Say an example of the pneumatic actuators, they can only go as high as 160 degrees. So on a steam valve, they must have a yoke. Valve size is another one to consider. Our positive positioner, is that required on our valves? And will the valve that I choose, does it have the linkage for a positive positioner? All of those must be taken into account before you can select the proper valve. Here's an application of taking the CVs and splitting them into a 1/3, 2/3 application. As an example, you see I have a very large valve here, CV of about 60. This is probably going to be a cast iron valve, therefore very expensive. Also, it's not going to be very good control. So what can be done is as follows. We'll break that 60 into a 1/3, 2/3 valve arrangement. Or in this case, you see CV of 20, a CV of 40. Why? For better control. During the majority of the year, I'm under light load conditions. Therefore, my 1/3 valve will be modulating to maintain that. When I hit my design condition, then my 2/3, or close to it I should say, then my 2/3 valve will start to open up. So you can see the advantages of a 1/3, 2/3 application is better control. Also, it is a relatively inexpensive replacement cost. It's much cheaper to replace a smaller valve in the 1/3, 2/3 than one very large valve. The disadvantage, though, it's an expensive initial cost. Now we're ready to select a complete valve assembly. Let's go through a problem so you can see how this is done. The example here is as follows. I want a small GS, that stands for globe screwed, valve. Stem up open, or that's a normally open valve. Pressure drop across the valve is going to be 9.2 feet. Now 9.2 feet, if you were to multiply that times 0.433, you'll come up with a valve, or I'm sorry, a pressure of 4. That's 4 psi. Now the gallons per minute is going to be 16, and we have 20 psi main supply. That's talking about a pneumatic system, 20 psi main, and we need a close-off pressure of 10 psi. And I'm going to be proportional, varying the flow. The first thing I want to do is calculate my CV. Again, CV equals your gallons per minute divided by the square root of the pressure drop. In this case, our gallons per minute is 16. Also, I'm already told what my pressure drop across the valve should be. It should be 4. The square root of 4, though, is 2. So our CV comes out to be 8. So I'm looking for a CV of 8.0. Here are the other things we're going to be determining. I want to know the valve body, the valve linkage, the actuator, and the valve assembly. This information is going to be gathered from the valve selection guide. As you can see here, as we go on down, here's the index for this guide. And in this index, you can see I'm going to take the valve that is first off two-way valves, which are these. And in this, it says globe screwed, stem up, normally open. And it says go to page 4.1. This is taken from page 4.1. And there are really 3 parts. One describes the valve, as you can see here. The second one talks about the CV, and the third talks about the actuator. First, let's look at the valve itself. Here it says VB9213 and a VB9223. The difference between them is one's a normally open, one's a normally closed. As you look down here, you can see all the other specifications for the valve, whether you're going to use it for steam, for water, what the temperature limits are, what the disc composition, what the stem is, and so forth. So our example that we want a VB, and reading the numbers right off, VB 9213-0-4-, and then it comes with a P. That's the port code. If you go down here to the number 2, we're going to look for our CV. This is our calculated CV. We're looking for something as close to 8 as we can get. In our example, 8 is right here. So we want a CV, or a port code rather, of 7. It has 8.2. That means a port code of 7. So I put a -7. Once you've determined what type of valve to use and the port code, the third thing is to choose an actuator. Now the actuators sections are divided into 3: pneumatic, electronic, and electric. Here we have the pneumatic section, and we're going to take a look at our valve. In this case, it was a 9213-7, which is right here. All these ratings that you see, all these little numbers, is the close-off pressure rating. Now on the valve I wanted, it was a normally open. And a normally open valve, by itself, will want a 3 to 7 or a 3 to 8 spring range. So that's this column. Also, it shows the 15 or 20 psi supply. In our example, we have a 20 psi supply. Going along here, you can see that my close-off pressure rating using this actuator is going to be 75 psi. Now, it needs to go greater than the close-off pressure rating that you needed. We needed a close-off pressure rating of 10. This has a rating of 75, therefore it's quite adequate to close off against the flow. Therefore, we're going to take this series of actuators, which in our example is series 200. The last step in finding the complete valve assembly number is as follows. We chose a series 200 actuator, which is right here. Notice it says stem up, and it has three ranges, 3 to 7, 5 to 10, or 8 to 13. We chose the 3 to 7. Going across from that, you'll see an actuator, or a actuator code number, in this case 201. Notice also right to the right of that it says there's our actuator, the MK2690. Taking this 201 though and dropping straight down, right here is our complete valve assembly number. Notice there's also the linkage here. But just to give you the complete valve assembly number and what it is, it's V, K, valve, and the K represents that it's a pneumatic assembly. The valve number stays the same, 9213 dash, and now I have the actuator code number, 201 dash 4 dash, and our port code in our example was 7. This complete valve assembly number will give you the valve, the actuator, and the linkage combined. Now, if you do not wish to order a complete valve assembly number, you can order the parts separately, and they are listed here. You can see there's the linkage, AV400, the actuator number, MK2690, is written there, and the valve number we've talked about before. You could order these separately and put them together yourself. The information covered in this tape was quite rapid, and some of it perhaps you weren't able to see. If you have any questions though, please consult Engineering Bulletin CA28, which is our control valve sizing.
As engineers design complex mechanical systems into today's buildings, properly designed ventilation systems are critical in providing a comfortable environment and acceptable indoor air quality. Proper fan selection and duct design is important whether designing office buildings, schools, hospitals, warehouses, or commercial retail space. Now let's examine how duct design and installation can affect fan performance. Normally, a fan is tested with an open inlet and a section of straight duct attached to the outlet. This setup results in uniform airflow into the fan and efficient static pressure recovery on the fan outlet. To observe the movement of air molecules in the duct, we've introduced helium-filled bubbles into the airstream. When space constraints do not allow for a section of straight duct, an elbow must be placed near the fan outlet. But look what happens. This installation results in an abrupt change in direction of airflow. It causes turbulence within the fitting. One bad connection can reduce airflow significantly below the fan's catalog performance. To calculate airflow in the duct, we've installed an airflow measuring station. This duct configuration is a reproduction of a test setup from AMCA Standard 210. Unrestricted, this fan delivers just over 1800 CFM. Now we'll add an elbow to the duct. Notice the turbulence within the fitting. It causes significant pressure drop. In this example, simply by adding one elbow to the system, airflow has been reduced approximately 25%. One way to improve the efficiency of air movement through the fitting is to install turning vanes in the elbow. The airflow is less turbulent and more uniform at the discharge of the fitting, resulting in a lower pressure drop. In this case, the airflow has only been reduced about 6% from the fan's initial performance. Many designers prefer utilizing radius elbows. In this test, this is the most efficient fitting of the three. The reduction in airflow is less than 4%. Originally tested with an open inlet, this fan delivered just over 1800 CFM. In many cases, air is ducted to the inlet of the fan. For proper performance, air must enter the fan uniformly over the inlet area in an axial direction without pre-rotation. This results in an airflow reduction of less than 1%. Occasionally, space limitations do not allow the designer to provide a straight inlet to the fan. Many times, this type of fitting is attached to the fan inlet. With this type of duct connection, a counter-rotating vortex appears. In this case, airflow has been reduced approximately 45%. Non-uniform flow into the inlet is the most common cause of reduced fan performance. These conditions alter the aerodynamic characteristics of the fan so that its full airflow potential is not realized. Listen to the pulsating sound of the fan. Notice that the fan is hunting, trying to find a stable operating point. The loss in performance with this type of connection is obvious. This loss is often referred to as system effect. To make matters worse, it cannot be measured. To select and apply the fan properly, these effects must be considered, and the pressure requirements of the fan must be increased. Fortunately, there is a better way. A sweeping radius elbow at the inlet provides a more efficient solution. In this case, the airflow has been reduced around 3%. By inserting a straight section of duct, the airflow is now just 2% below the fan's catalog performance. In summary, proper fan selection and performance can be achieved if calculated duct losses as well as system effect factors are considered during the design stage. At Lauren Cook Company, we are committed to meeting the customer's needs while leading the industry in quality. This begins with the application of the most sophisticated design tools available, including computational fluid dynamics, finite element analysis, and three-dimensional solid modeling. Fan performance is then verified in our AMCA registered laboratory. Production quality is assured through a combination of the latest in CNC controlled equipment and a highly skilled and dedicated workforce. Our commitment to quality is demonstrated by Lauren Cook Company's ISO 9001 certification.
2 will go to the first antibonding molecular orbital, 2 will go to the second bonding molecular.
Energy management begins with wise management decisions. Hi, I'm Al Zajac. Today, the installation of a variable air volume system is a popular energy conservation decision. Variable air volume systems, however, need to be continually controlled in accordance with the demands of the system. Due to the popularity of variable air volume and the need for the associated controls, this videotape has been developed. It will address the fundamentals of variable air volume, the sensing of pressures within the duct, and control of the central system. You might wonder, why select a variable air volume system? The reasons are simple. A variable volume system is more energy efficient than a constant volume system in two significant areas. One is the reduction in fan horsepower. The second is the resultant decreased load on the mechanical cooling equipment. The following chart presents a sample load calculation for a constant volume system. This system, in the following example, is for an interior cooling only zone. Let's take a look at an interior office area. And let's say that that office area is made up of 2,500 square feet. The desired space temperature is 75 degrees. Our central system discharge temperature, 55 degrees. Let's now consider each one of our loads, beginning with our lighting load. Our lighting load is 10.3 BTU per hour per square foot, giving us a total of 25,750 BTUs per hour. Our people loads are dependent upon the population density within the building. And let's say that we have a population density of 30 square feet per person at a total of 250 BTUs per hour per person. This will give us a load of 20,850 BTUs per hour. Our equipment loads are at 1.7 BTUs per hour per square foot, giving us 4,250 BTUs per hour. The total of the preceding loads amount to 50,850 BTUs per hour. To this, we will add a 20% peak load factor of 10,370 BTUs per hour. Our total load is 61,220 BTUs per hour. As true of many systems, the constant volume system just described was sized with a 20% peak load factor. Generally, this peak load condition will exist less than 10% of the time. Therefore, the system will be extracting an excess of 10,370 BTUs per hour from the space. As a result, the space temperature will drop. There are two ways to compensate for this space temperature drop. One, reheat the air, or two, reduce the volume, CFM, of the air. Shall we reheat the air? No. Let's look at this calculation to prove my point. The additional cost of reheating the air equals 10,370 BTUs per hour times 10 hours per day times 260 days per year times $4 per million BTUs, which equals $108 a year, based on occupied time periods. Shall we reduce the volume of the air? Yes. First, as a result of varying the volume, we will reduce the sensible and latent loads on our cooling coil and chiller. Secondly, savings will be realized due to reduced fan horsepower requirements. Now that the savings from VAV systems are evident, let's address the fundamentals of variable air volume system control. Automatic controls for variable air volume systems must, 1. Maintain temperature difference between the heating and cooling mediums at maximum economical levels. 2. Conserve fan horsepower. The supply and return fans must be throttled as the system load is reduced. 3. Maintain supply duct static pressure at a constant minimum level. This reduces the possibility of high pressure drops within the system, which could cause objectionable noise. 4. Maintain the volume differential between the supply and return fans equal to the volume of the exhaust from the space. This is done to prevent the HVAC system from causing building pressurization problems. 5. Produce system stability. Types of systems. There are 3 basic types of variable air volume systems. 1. The all-air variable volume system. 2. The terminal reheat variable air volume system. And 3. The dual duct variable air volume system. Buildings may contain any combination of the 3, since it is the terminal unit performance that varies. One central system could then contain terminal units of 3 varieties. 1. All-air variable volume systems supply cooling only to spaces. Upon a change in load, the room thermostat's output pressure varies to modulate the terminal unit damper. It should be pointed out that the room thermostat is the master and that it readjusts the submaster flow controller. The purpose of the submaster is to compensate for changes in flow that may result from changes in duct static. Heating is not available from these systems, since they are cooling only. They serve interior zones only. If some means of overcoming the heat loss through exterior building walls has been provided, these systems may be applied to exterior zones. On this graphic of an all-air variable air volume system, remember the following conditions exist. 1. Cooling only available to the space. And 2. They are utilized in interior zones. System type number 2. Terminal reheat variable air volume systems operate similarly to the preceding system. However, when the heat gain in the space drops or the heat loss from the space increases to a point where the terminal unit's volume has reached its minimum, generally 40% to 55% of design maximum, heating is introduced by the reheat coil. These systems are generally applied to exterior zones. Any introduction of heating to an interior zone which has no heat losses would be considered an energy waste. On this graphic of a variable air volume system with terminal reheat units, remember the following conditions exist. 1. Heating or cooling available to the space. 2. Exterior zones only. System type number 3. Dual duct variable air volume systems have hot and cold air available to the terminal units at all times when the space temperature is at the low end of the thermostat's throttling range. The terminal unit's hot duct volume damper is open and the cold duct volume damper is closed. Upon an increase in load or a decrease in heat loss, the hot duct damper modulates close. When the terminal unit's volume has reached its predetermined minimum setting, and upon a further increase in space temperature, the hot duct damper shall close and the cold duct damper shall open, maintaining the minimum volume. Upon a still further increase in space temperature, the cold duct damper will modulate to its fully open position. Minimum settings can be as low as 0%. These settings will vary with the space exhaust and ventilation requirements and with diffuser characteristics. In this dual duct variable air volume system graphic, 1. Heating or cooling is available to the space and serves exterior zones only. Next, let's address the sensing of pressures within the duct using the various types of pressure sensing tips. The accurate sensing of pressures in an all-air system is important when controlling the pressures in a duct. However, to get accurate sensing, certain things must be considered. First, which pressure is being sensed? Static, velocity, or total pressure? Then the proper sensing element must be selected and properly located to give the most accurate reading. Now, let's consider these three pressure sensing areas. The first type, total pressure sensing. At any cross-section in a duct, the total pressure, PT, is the sum of the static pressure, PS, and the velocity pressure, PV. This illustrates the method of measuring total pressure. The second type, static pressure sensing. Static pressure is defined as that pressure within a system exerted in all directions, but measured at right angles to the direction of the airflow. Static pressure is the potential energy within an air system. And the last type, velocity pressure sensing. Velocity pressure is defined as that pressure within a system exerted in only the direction of the airflow. It is sensed as the difference between total and static pressure. Velocity pressure is the kinetic energy within an air system. When sensing a static total pressure or their difference, velocity pressure, a standard pitot tube can be used if the velocity component can be isolated. Shown here is a detailed drawing of a pitot tube. The pitot tube combined both static and total pressure openings in a single instrument. The pitot tube is inserted in the airstream parallel to the direction of flow and with the opening always pointed into the airflow or upstream. The opening in the center of the tube is connected to the inner tubing and registers the total pressure on a manometer. The outer tube has a number of small radial holes in its wall, and the space between the two tubes conveys to the manometer the static pressure. The velocity pressure, as discussed, is the difference between the total pressure and the static pressure. These devices have proven to be the most reliable for end-of-duct static pressure sensing. A field-fabricated velocity pressure sensing tip can satisfactorily control the volume of air being delivered to a space. The field-fabricated tip, as shown here, provides control accuracy almost equivalent to a standard pitot tube. However, it should not be used as an indicating device since it does not measure a true velocity pressure. When locating a velocity measuring tip for purposes of control, it is important to select a portion of the duct in which the flow pattern and pressure distribution are relatively constant. A total pressure sensing tip can also be field fabricated as shown here. For total pressure measurement, The tip is pointed directly into the airstream. For static measurement, the tip should be fabricated and located at right angles to the flow as shown here. Whether it be for the purpose of maintaining building pressurization or for other reasons, the need for sensing proper outdoor air pressure is sometimes important. The questions which usually arise are how to construct and locate an outdoor air pressure sensing head in order to obtain a fairly stable reference pressure. Shown here is a dimensional drawing of an outdoor air atmospheric pressure sensing head. It can be field fabricated with two square plates which are placed 1/4 inch apart with a small 1/16 inch diameter pickup orifice in the center of the lower plate, as shown here. The plates are spaced 1/4 inch apart in order to prevent the velocity component from reaching the 1/16 inch diameter pickup orifice. Airflow perpendicular to the pickup orifice is near laminar, greatly reducing unstable reference pressures associated with turbulence at or near the sensing location. In addition, a hollow 1-inch diameter pipe stand used to support the sensing head will act as a dampening chamber to further dampen sudden pressure changes caused by wind gusts, etc. An important consideration is where to locate the outdoor air sensing head. Locating it on the side of a building is undesirable due to drastic pressure changes caused by wind direction, etc. The logical and most satisfactory location then is the roof of the building. Unfortunately, this location is not without its complications, again due to the behavior of wind as it flows around and over a building. Wind action against the building creates a low pressure area above a building. Thus, it is good practice to mount the sensing head some distance above the roof line to obtain as representative an atmospheric pressure as possible. For best results when using single point sensing, it is recommended that the sensing head be installed at least 20 feet above the roof line of a building in an attempt to point the element above the negative cavity caused by airflow in high winds. To avoid the negative cavity problem, installation of two reference tips on opposite top corners of the building will provide the best results when sensing atmospheric pressures. This method, utilizing the higher of the two signals provided from the differential pressure transmitter connected to these sensors, will provide a relatively accurate atmospheric reference while substantially reducing the height above the building the sensing tips are to be locating. Now, let's look at multiple point self-averaging pitot tube stations. Multiple point self-averaging pitot tube stations were introduced to the commercial control industry for use in controlling and indicating air volumes. When installed in the ductwork at distances from the cause of air turbulence, as specified by the manufacturer, accurate sensing of total and static pressures is achieved. The unit manufacturers claim that the air straightening devices eliminate air turbulence and rotational airflow by directing the air into a near laminar flow. The distance from a major air turbulence will determine the type of sensing station to be applied. The stations are generally broken down into two categories, fan and duct, the difference being the size of the honeycomb air straightening section. The fan models have smaller diameter honeycombs than duct models, providing better air straightening capabilities. It should again be mentioned that these devices must be installed at proper distances from the cause of turbulence, at least equal to or greater than that recommended by the manufacturer, or sensing accuracies will fall short of the plus or minus 2% accuracies claimed. A point often overlooked. These units also have maximum and minimum velocity limits. above a maximum velocity of 4,000 feet per minute and below a minimum velocity of 700 feet per minute, these units will not function as specified. Therefore, single point sensing of duct static pressures in end-of-duct applications will be acceptable, not to mention much less expensive. However, a point must be chosen where airflow is relatively straight, thereby reducing the possibilities of a velocity pressure component being sensed. Looking back, we have addressed sensing pressures and the basic types of VAV systems. Now, let's get more specific and address the methods of controlling fan discharge. The first method concerns constant volume control. With constant volume systems, the fan is initially set up to operate in accordance with the selected point of operation from the fan characteristics. Fan control of constant volume systems is, for the most part, non-existent. Peak loads are summed up during the time of system design, and the fan is selected and initially adjusted accordingly. Next, we have a number of options when controlling variable volume discharge. Variable volume systems, however, need to be continually controlled in accordance with demands of the system. A fan is designed to discharge a given capacity at a given horsepower. In a variable volume system, the amount of air needed is dependent upon the indiscriminate action of the terminal units. Without continuous feedback control, the fan will always deliver full capacity at full horsepower and produce larger than necessary static pressures at the terminal units. Horsepower is indeed wasted and operational savings are not realized within proper control schemes. When a control system is used to reset the fan capacity in accordance with the demands of the system, excess static pressure at the terminal units is eliminated and the fan system horsepower adjusts accordingly to provide operational savings. There are 4 common methods of controlling the effects of the fan. 1. Discharge damper control. 2. Inlet vane control. 3. Variable pitch control. And 4. Speed control. Shown here are the approximate power savings which can be obtained by reducing air quantities for the 4 methods of capacity control. On the graph, a percent of power input is shown plotted with the percent of rated fan volume. From a power consumption standpoint, variable speed motors and blade pitch control are the most efficient. Inlet vanes save some power, while discharge dampers throttling at the fan save little. From a first cost standpoint, dampers are the least costly. Inlet vanes and blade pitch control follow, with variable speed motors being the most expensive. The first option is discharge air dampers. Discharge dampers are installed to add resistance at the fan, which no longer exists out in the system when flow decreases. The purpose of the discharge damper arrangement is to create an excess pressure drop near the fan, thus permitting smaller pressure drops at the terminal units. The amount of air delivered to the terminal units is dependent upon the pressure built up at the fan. When air delivery has to be reduced at the terminal unit air damper will throttle the fan down. It is rather unpractical to have the terminal units throttle down 3 inches of water gauge when all they should have to throttle down is 1 inch of water gauge. So, the pressure over and above what is actually needed at the terminal units is throttled down by the discharge dampers before it ever enters the rest of the system. Because of the initial throttling, there is less noise at the terminal units. With an initial pressure drop at the fan, there is more ductwork prior to the discharge to aid in sound attenuation. Sizing of discharge air dampers should be done with great care. There are many rules of thumb, but the recommended procedure is to size the discharge air dampers for a wide open pressure drop of from 7 to 10% of the system pressure. Variable air volume systems should not be controlled with discharge dampers if operational efficiency is desired. Discharge air dampers waste horsepower. One of the main objectives in applying a variable air volume system is to save on operating costs. With discharge air dampers, efficiency is not adequate to warrant their use for purposes of economic operation. In summary, it is recommended that discharge air dampers be avoided for control of variable air volume systems. The next option is variable inlet vanes. They are the most commonly used method of controlling fan capacity on variable air volume systems. Inlet vanes, often referred to as pre-rotation vanes, cause the air to swirl before it enters the fan wheel. The fan wheel cannot grip the air as well, and consequently capacity is reduced more efficiently than with discharge damper control. Excess pressure is not created and wasted. Shown here is the effect of an inlet vane type system. The fan inlet vanes are positioned by an actuator in response to a signal received from the system's static pressure receiver controller. The static pressure transmitter, through the receiver controller and actuator, repositions the inlet vanes to maintain a relatively constant duct pressure at the point of sensing. As the terminal unit dampers throttle, the characteristic curve, the resistance curve, shifts. The pressure senses this shift, and thereby the inlet vanes are throttled accordingly, shifting the fan curve, and in turn establishing a new operating point. The new operating point of fan operation will depend upon where the terminal units being throttled are located in the system. Fan discharge pressure will not remain constant since the location of the pressure transmitter is at the end of the system. Care must be exercised in selecting the fan. It is important that the fan can be throttled to the near minimum flow required without becoming unstable. Systems that can be throttled to near shutoff must often be equipped with a fan bypass to permit a minimum flow through the fan at all times. A third option for controlling fan discharge is variable pitch blades. Variable pitch axial flow fans deliver an amount of air in accordance with the pitch of the fan blades. As more or less air is needed in the system, an actuator positions the pitch of the fan blades accordingly. The positioning of the blades is similar to the positioning of the inlet vanes. However, the fan is always spinning. Inlet vanes remain stationary. The degree to which the blades are pitched determines how much air can be gripped and passed on into the system. Lastly, the fourth option is variable speed drives. There are various ways to control fan speed. Common methods include variable speed motors, magnetic couplers, and fluid drive systems. Fluid drive units use hydraulic fluid for transmitting power. Magnetic coupler models use interacting magnetic fields to transmit power. Another method is to use exhaust steam, when readily available, to drive the fan with a steam turbine. The most common method, however, is electric motor speed control, which is accomplished by varying the frequency of the input power. In any case, fan speed control is accomplished by mechanically, electrically, or hydraulically varying fan RPM in response to the signal from the pressure transmitter in the system. The last segment of the program deals with flow and pressure controls. There are two basic reasons for applying system flow and/or pressure controls to a variable air volume system. First, to conserve fan horsepower, the supply fan must be throttled as the system load is reduced. This is accomplished by static pressure control of supply fans. For purposes of this discussion, let's deal with single duct VAV systems. The supply fan is normally controlled from the end of the longest duct run. The philosophy being that if we maintain a minimum pressure at that point, all other parts of the duct will be at a high enough pressure to deliver designed flow. Since control of the supply fan does not directly affect building pressure, stability of control is really the only major criteria for controller selection. Unfortunately, stability often dictates low controller gains, resulting in wide throttling ranges. The wide throttling range is often objectionable. In this case, controllers with automatic reset should then be applied. This type of control will automatically reset back to set point. Our second reason for system flow and pressure controls is because the return fan must be throttled to match the reductions in supply capacity in an effort to maintain building pressures at an acceptable level, ideally equal to atmospheric pressure. This reduces leakage of outside air into or out of the building. Remember, all outside air which enters the building, whether through outside air dampers or the porous structure, must be tempered with additional energy expenditures. How close must the return fan track the supply fan is difficult to determine. Items affecting building pressure are the porosity of the structure, CFM of all the constant exhaust in the structure, how ventilation codes are being met, and what is the acceptable building pressure. Although the amount of air supplied to and drawn from a closed area within a building will determine relative pressure, it is the amount of outside air introduced into a building as compared to the amount being exhausted that determines the overall building pressure with respect to atmospheric pressure. This fact seems to elude many specifying engineers, and the tendency is to concentrate on the supply and return fan volume control only. By now you are probably wondering, what affects building pressure? Obviously, the answer to that question is how much air is being introduced and how much is being exhausted. The difference should pressurize the building and leak out through the cracks. Therefore, the size of the cracks or porosity of the structure is also a factor. Since some factors are controllable and others are not, the following list of factors must be considered. 1. Building porosity. 2. Stack effect. 3. Wind velocity and direction. 4. Constant or variable exhausts, such as from lavatories, kitchens, etc. And 5. The amount of system air introduced and exhausted, which is affected by A. Differences in supply and return fan CFM, and B. Damper characteristics. Now that we understand what affects building pressure, let's address the methods of controlling building pressure. First, direct building pressure control. Since building pressure is the basic reason for matching building supply and exhaust, the most obvious and most straightforward control arrangement would be to sense building static pressure and attempt to match it to atmospheric conditions. Since this also eliminates infiltration or exfiltration, it also is the most economical from an energy standpoint. Obtaining a stable atmospheric reference is often difficult. It depends on building shape, size, location, and wind patterns around the building. However, the effort is very rewarding when one considers how simple the control system would be. Control supply fans from a point in the duct which permits least energy use at the fan, and control the return fan capacity to maintain building static. Each year, more experience is gained. More work is done to study pressure patterns around the building exterior, and more successful installations continue to operate. Shown here is the latest successful attempts at obtaining stable atmospheric references. The method for the pressure sensing is basic. The flow and pressure patterns indicate a near atmospheric pressure at the building's edge on the windward side. Selecting two opposite corners assures one pickup in a most ideal location. The next method of building pressure control, supply and return fan matching, can be achieved by fan capacity matching through balancing. Where single sets of supply and return fans are employed, the signal controlling the supply fan can also be used to control the return fan if the system startup is entrusted to a good balancing contractor. With adjustment of the starting point and span of the return fan actuator, the capacity of the return fan can be set at the desired value at two different system volume levels, usually 100% and 60%. A pilot positioner with adjustable span and starting point permits adjustment of the return fan capacity for perfect match at these two system capacities if fan and capacity modulating devices have similar characteristics. Volume differences can be maintained within close tolerance. On these simple systems, this control arrangement has been very successful. The subject of return fan control goes beyond the simple methods we have just discussed. Very sophisticated control schemes can also be applied to obtain even greater accuracies and thus improve control and energy savings. Return fan control can also be accomplished by a control scheme known as velocity pressure matching. This type of control may also be called any one of the following names: constant volume differential, return fan tracking, or return fan synchronization. In any event, this subject is far too detailed to address in this program. To summarize what we have learned in the program, let me review some major points. Variable air volume systems produce savings at the mechanical cooling equipment and also at the fan. We explained types of VAV systems, pressure sensing tips, methods of controlling fan discharge, flow and pressure controls, and lastly, the methods of controlling building pressure. Thank you for your attention during the program.
Back on and fill up the tank. There's not a whole lot of room in the master bathroom, so we're setting up the sinks and the whirlpool here in the bedroom. Besides, it's a lot easier to attach the faucet and the tail pieces before the units go in place. Now this sink is made out of vitreous china, and on this model we've got 3 openings, for the faucet and for the control handles. And the control handles are 8 inches apart. The valves in the faucet in this unit are connected by this flexible hose, and the water supply lines will connect in here. And this is how the stopper works.
Well, we'll show you how it all goes together as we work on our second sink here. It's a lot easier to do if we clamp it in position. Why don't you go ahead and tighten that down there. First, we secure the spout and the hot and cold water valves. Handles go over the adapters on each valve stem, and they're secured with screws. We connect the supply hoses to the spout through the T in the middle, and coupling nuts secure the hoses to the hot and cold valves. Now, installation varies between models, so be sure to follow instructions that come with your assembly.
The drain connects the sink with the trap and the drain pipe, and we put a ring of plumber's putty around it. Now I can just slip it through the opening.
And we use a slip nut and washer to secure the tail piece here to the drain from underneath. We put a gasket in the coupling for our drain stopper and put that on. And once it's secure, we'll line it with the back of the sink. And we'll tighten our slip nut in just a second. There we go.
The stopper lift arm slips through a hole in the top of the faucet, like that. And then the stopper itself can go down through the opening in the drain.
And then we hook up the stopper linkage. If you hold that still there. And we just hand tighten this for the time being.
All right, now pull the drain open so we can adjust the stopper arm. That looks good.
And tighten it down.
Works.
Perfect. These are self-rimming sinks, which mean they sit directly on top of the countertop.
They came with a template that helped us cut the openings to the right size.
Now we're ready to hook them both up to the plumbing. We'll start with the supply lines, which means hooking up the faucets to this flexible tubing with a 1/2-inch coupling to the faucet and a 1/4-inch coupling to the shutoff valve. Now it gets a little cramped in here, but it should go pretty quickly. We just screw down one end of each of the supply lines over the control valve like so. And we tighten it a bit. And screw the other over the opening on the shutoff valve. All right. Now, next thing we want to do is hook this trap up to the bottom of the sink and this waste arm into the stub out in the wall. But first, we'll have to glue this adapter onto the stub out. The adapter will allow us to attach the waste arm adapter to the waste arm quite long enough with a piece of AB. I work the pieces so, then turn on the lines and test them.
About done with that outlet?
Yep, I've got it.
Good. Attaching the sink here shouldn't be too tough.
Yep, we don't have any water pipes to sweat.
Oh, that's true. Just that plastic pipe to glue in.
Yep.
We've already put in the hot and the cold water pipes and the drain pipe underneath here. Now we need to finish the process by connecting all these stub-out pipes to the sink, disposal, and dishwasher. We're using a special type of shutoff valve for the hot water here. It's got 2 outlets. One's for the sink, one's for the dishwasher.
A double sink like this is pretty common in most kits, a wide variety of styles and faucet choices. Now, it's a good idea to follow the directions on how to install these faucets pretty closely because they're all different. Luckily, the drain assemblies are pretty much standard. Put some plumber putty around like so. Jojo, could you help me lift up the sink here?
Sure.
Okay, let's get this up like so.